So let's do a zero force member example here. This is really fast because remember, this is all visual. So there's not really any calculations behind this or anything. Let's look at the two-member scenario. So if we have any spot where there are two members framing in and only two members framing in, and there is no point load and no support. So if I'm looking through here, I've got a bunch of members in the support there. I've got three. We'll come back to B later. Here's another one that we'll come back to later. There's all kinds of stuff going on there. C is not going to tell us anything. F, E, no. But D, yes. Joint D is a joint that has two members framing in. There is no point load applied at D, and there is no support reaction at D. So that tells me that DE and CD have to be zero force. I know that there is a force applied over at the E end of DE. I don't care. The zero force process, you look at ends. So I beg you to train your eye to look towards the more simple ends of members. Don't worry about the complicated ends. One thing that is not going to help me at all in this problem is probably joint C, because look at all this business. There's 1, 2, 3, 4, 5, 6 members framing into C, and it's a pin support, so there's two support reactions. There is all kinds of big hot mess there at C. And while it's perfectly important to the truss, it doesn't help me figure out what is a zero force member. But if I look over at the simple end of member CD, the D end, there is nothing going on at D that can make member CD have force. So even though there's all this other business going on at joint C, guess what? CD is not part of it. CD is like, I got nothing, guys. You guys have fun with us. And so now C only has 1, 2, 3, 4, 5 members framing into it, because they are both zero force. So I'm going to draw zeros over them. And for the rest of the exercise of solving for member forces or cutting free bodies, I don't even need to draw them if I don't want to. I can draw them and put a zero over them. That's fine. But they might as well not even be there. Now, the next step. Let's look at scenario 2, where we have 3 members framing into a node, 2 of which are collinear. So B is one of those. I have 2 collinear. I have AB and BC are collinear to each other, and BJ is non-collinear, but there's only 3 members framing in at B. So that's telling me that BJ must be zero force. Similarly, up here at G, I have GH and I have FG that are collinear. I have CG, which is non-collinear. There is not a support reaction at G. There is not an applied load at G. So that means that CG is also zero force. Now, we've done all this work. We're very proud of ourselves. We think we're pretty cool. Let's keep going here. Is there any other place that maybe we need to look at? What about joint E? Joint E has 2 collinear members and then another member coming out. Actually, it doesn't even have 2 collinear members, right? Because this one's zero force over here. So really, it only has 2 members framing in. But look, there's an applied load. So we're not going to learn anything at joint E. Are there any other places? Well, realizing that BJ has been deleted because it's a zero force member, let's look at joint J now. And joint J now has CJ, HJ, and AJ framing into it. So it has 3 members framing in, 2 of which are collinear. So that makes the 3rd member here. AJ has to be a zero force member. So those, I believe, are all the zero force members in this truss. All the other ones, it's not that the other ones won't, that you could potentially calculate one of them to be zero in a weird situation, but these are the obvious standouts that are definitely zero without doing any calculation. So I hope you see how important zero force members are, because this truss is now 1, 2, 3, 4, 5 members simpler. And that's a significant portion of this entire truss. So if you were asked to solve for all of these members, you just, in one slide here, got rid of a whole lot of heartache.